Hello everyone, I'm Liu Songyuan from Beijing Institute of Technology. I'm very pleased to be here to introduce my work. The topic of my presentation is modeling of a 6-bar Tensegrity robot using the Hamiltonian framework and experimental validation. The presentation is divided into 4 sections. First, we introduce the background and motivation. The 6-bar tensegrity robot is composed of 6 rigid bars, 12 nodes, and 24 controllable tensile cables, featuring stability, adaptability, and the ability of active deformation and rolling. The aforementioned advantages enjoy tensegrity robots with significant potential in tasks such as climbing, pipeline inspection, planetary exploration, and airdrop. Consequently, research on their modeling and control is gaining increasing attention. The 6-bar tensegrity robot features nodes located at both ends of each bar. Each node is connected to four neighboring nodes by cables. Servos are attached to the bars, which can pull the cables. Here, we present a demonstration of the rolling motion. Let's talk about the modeling of tensegrity robots. As a type of soft robot, tensegrity robots can change their configuration and node positions by actively adjusting the internal forces within the structure. During deformation and rolling, the robot's nodes come into contact with walls, the ground, and other surfaces. The resulting contact forces affect the robot's motion. This indicates that tensegrity robots possess complex dynamic characteristics, which pose challenges for modeling. A complete dynamic model should be able to describe the motion of nodes under the influence of internal and environmental contact forces. However, the existing results have some shortcomings in meeting this requirement, including a lack of interaction with the environment, invisible control input, and no physical validation on the model. Therefore, we aim to address these issues in our work. Next, we introduce our main work, Hamiltonian dynamics. First, to model the interaction between the robot and the environment, we use the Hamiltonian framework. Based on the framework, the dynamics of tensegrity robots can be viewed as a model where the robot body exchanges energy with external parts, allowing us to integrate various forces into a unified form. The robot body is regarded as a Hamiltonian system, with its energy comprising the kinetic energy of the bars and the potential energy of both the bars and cables. Additionally, the constraints imposed by the fixed bar length must be considered. Based on the system's energy and the Hamiltonian dynamics framework, we can derive the differential equations governing the generalized coordinates and momenta. Based on the node and the bar matrix, we first calculated the translational velocity and rotational angular velocity of a single bar. Then we determine its kinetic energy using the initial matrix and obtain the total kinetic energy of the robot system. The potential energy includes two components: the gravitational potential energy of the bars and the elastic potential energy of the cables. The gravitational potential energy depends on the height of the bar's center of mass, while the elastic potential energy is calculated based on the elongation of the cables. To model the actuators, we define UK as the elongation of cable K pulled by an actuator. When the cable is pulled by an actuator, the elastic potential energy changes. Apply the changes to the Hamiltonian dynamic equations. It can be seen that the changes in the momentum differential equations represent the forces exerted by the actuators. To calculate the interaction between the robot and the environment, we introduce a continuous contact force model, which consists of friction and normal contact force. The calculation of frictional forces applies the principle of Tokyo balance, allowing the pressure distribution to be computed in real time based on the position of the center of mass. The Hertz contact model is introduced to calculate the normal contact force when the robot makes contact with other surfaces. To accurately calculate the normal contact force, we collected data on the contact process between nodes and ground, including contact velocity, deformation, and contact force. Subsequently, we used the least squares method to identify the parameters of the Hertz model. After completing the modeling of the robot body and external parts, we derived the full dynamic equations based on the port Hamiltonian framework. Next, we present our simulation and experimental results. To run the simulation, we make the definition of nodal indexes and design the calculation loop to solve the dynamic equations. Then we implement data visualization in MATLAB. The figures show the simulation results of the robot's deformation and rolling. Regarding the experimental setup, the physical experimental environment includes a computer that sends control commands to the prototype. A motion capture system collects the position of markers mounted on the prototype, and after processing, it provides the bar positions and orientations back to the computer. In the experiment, we applied the same control inputs to both the prototype and the simulated robot. It can be seen that both exhibited consistent deformation trends and rolling behavior. Additionally, we make data comparison between the prototype and the simulated robot. The results demonstrate that the dynamic model has high accuracy. Finally, we make the conclusion of our works. The contributions of this paper include dynamic modeling based on the port Hamiltonian framework, the continuous contact force model, the actuator model, and experimental model validation. Future work could include model-based rolling control and continuous rolling motion planning. Thank you for listening.